Continuing from wherever we left last time, we are going to talk about the equilibrium of an object. So, an object is said to be in equilibrium if a number of forces acting on it produce no change in its state of rest or of uniform motion. Also, the motion may be rotational or translational. The three kinds of equilibrium that we are going to study are static equilibrium, dynamic equilibrium, and neutral equilibrium. First one, static equilibrium. A body is said to be in static equilibrium. Remember, static means stable. It is in a stable equilibrium if a number of forces are acting on it, but the body is still at rest. Like I told you last time, if an object is in equilibrium, do not think that there are no forces acting on it. There are a number of forces acting on it, but the forces are acting such that the object is still at rest. In that case, the vector sum of all the forces acting on the object is zero. For example, consider a situation when a beam balance is balanced in a horizontal position. Now, everyone has seen a beam balance. Suppose if we put equal amounts of weights in both the pans of the beam balance such that it is balanced. That means the clockwise moment of the right pan is balanced by the anti-clockwise moment of the left pan, and hence the beam balance has no rotational motion. In such a case, beam is said to be in static or stable equilibrium. Another kind of equilibrium is dynamic equilibrium. When we use the word dynamic, we mean the object is in motion. It is not static, it is in motion. Dynamic equilibrium. A body is said to be in dynamic or unstable equilibrium if it remains in state of motion even when a number of forces are acting on it. Now, when we talk about dynamic equilibrium, the object is in motion. The main difference between static and dynamic is in static, there are number of forces acting on the object, still it is at rest. Dynamic equilibrium, there are a number of forces acting on the object, it is in a state of uniform motion. For example, when a body provided once in motion, then it moves on a smooth surface with a constant velocity and zero acceleration, and hence the body is said to be in dynamic equilibrium. The best example of dynamic equilibrium is consider a train that is moving on tracks with uniform velocity. When it is moving with uniform velocity, it is said to be in dynamic equilibrium. In this case, there are two forces acting. The forward acting force of the engine of the train is balanced by the backward acting drag of air or the frictional force of air, and hence the train is moving with uniform velocity. So that was a case of dynamic equilibrium. The third kind of equilibrium is known as neutral equilibrium. A body is said to be in neutral equilibrium if on being disturbed from its initial position, it stays in equilibrium in the new position also. For example, a cone is lying on a horizontal surface, moves along the slant height. Then it is said to be disturbed from its equilibrium position and it will acquire a new equilibrium position when it is released. We are talking about a cone that is lying sideways. If we move it, if we apply a force, it is going to be disturbed. but immediately it is going to acquire a new position and it will be in equilibrium position in the new position as well. So these are the three kinds of equilibriums. Next, we talk about conditions of equilibrium. There are two important conditions to be satisfied for an object to be in equilibrium. First one, the vector sum of forces acting on the body should be zero in all directions for translational equilibrium. Remember, when we are talking about translational equilibrium, we are not talking about turning effect. For example, a book is lying on a table. The best example is a book lying on the table. A book lying on the table does not move, not because there are no forces acting. There are two forces acting on it, but both the forces are balancing each other. Let me tell you what forces are there. When the book is lying on the table, there is a downward acting gravitational force acting on the book, while at the same time there is an upward acting normal reaction force acting on it. Now both these forces, the downward force and the upward force, are equal and opposite. So their vector sum is zero and hence the object remains in equilibrium. Second condition, the vector sum of moment of forces acting on the body should be zero for rotational equilibrium. Now we are talking about turning effect, right, for a pivoted object. So consider a beam balance which is pivoted at a point in the center. If its anti-clockwise moment of force is equal to its clockwise moment of force, then it will be in equilibrium, right? So the vector sum of moments of forces acting on this beam balance is also zero. So these are the two conditions required for an object to be in equilibrium. We are going to talk about principle of moments, which is a very important principle which talks about when does an object remain in equilibrium. So according to the principle of moments, if there are different kinds of forces acting on a body which is capable to rotate about an axis, but there is no rotation taking place, then we say that the sum total of anticlockwise moments is equal to sum total of clockwise moments. Again, we consider the same example of a beam balance. If the anticlockwise moment is equal to clockwise moment, then the beam balance would be balanced. But say if there are a number of forces acting, instead of one force acting on the left and one force acting on the right, there are two forces acting on the left and say three forces acting on the right, then the sum total of all the left hand side moment of forces should be equal to the sum total of all the right hand side forces. And in that case, if all the sum of anticlockwise moments is equal to the sum of all the clockwise moments, then the object will be in equilibrium. We are going to use the principle of moments when we solve the numericals. Next, we talk about center of gravity. Now, since we are talking about balancing and we are talking about how when a number of forces are acting on the object and still it is balanced or still it is in equilibrium, we have to talk about center of gravity of an object. So the first thing is the definition of center of gravity. Center of gravity of a rigid body is a point at which its whole weight is supposed to act. So in general, we say that center of gravity is the balancing point of the object. Now, the position of the center of gravity of any object depends upon three things. It depends upon three factors. Number one, the position of center of gravity depends upon the distribution of the mass of the object. That means whether the object is top heavy, whether the object is bottom heavy, whether the object is heavier on the left hand side or it is heavier on the right hand side. So the distribution of mass plays an important part in determining the center of gravity of the object. Number two, the center of gravity may be inside or outside the body. And the third one, if the body is of a symmetrical shape whose weight is distributed uniformly, then the center of gravity lies at its geometrical center. This one is true for all the correctly mathematically shaped objects. For example, a cylinder, a sphere, a triangular lamina, which are symmetrical in shape and whose weight is distributed uniformly, then the center of gravity of that object will always lie at its geometrical center. Let us look at some important examples whose center of gravity we are supposed to remember. So the first one is a uniform rod. For a uniform rod, which is a perfectly shaped object, its center of gravity is at its midpoint. For a circular shaped disc, again, center of gravity is its geometric center. For a solid sphere, for a sphere, it may be solid or hollow. The center of gravity again is its geometric center. For a cylinder, the center of gravity is the midpoint on the axis of the cylinder. For a circular ring, the center of gravity is outside the body, but it is at the center of the ring. For a rectangle or a parallelogram, the center of gravity is at the point of intersection of the diagonals. For a triangular lamina, the center of gravity is the point of intersection of its medians, which is also known as the centroid of the triangle. Two important shapes we are supposed to remember, a hollow cone and a solid cone. For a hollow cone, the center of gravity is at a height h by 3 from the base of its axis, while for a solid cone, it is at a height h by 4 from the base of its axis. And for solid shapes like cube and cuboid, the center of gravity is again at the point of intersection of the diagonals. So these are the shapes we are supposed to remember center of gravity for. Next, we are going to talk about uniform circular motion, which is a typical kind of a motion. Many questions in board are asked based on it. Uniform circular motion. Definition. When a body moves with a constant speed in a circular path, then its motion is known as uniform motion. However, we should remember that although the speed remains constant, its velocity is variable because the direction of motion changes at every point on the circular path. Remember, velocity is a vector quantity. It has a magnitude and it has a direction. The magnitude of velocity, which is known as speed, is remaining constant. But, however, the direction of velocity is changing at every point and hence the velocity is considered to be variable. Now, since the velocity is variable, we can say that the object is in acceleration and hence uniform circular motion is considered to be accelerated motion. You can look into this diagram which shows that the velocity is changing at every instant. Note, important. In uniform linear motion, speed and velocity both are constant and acceleration is zero. While in uniform circular motion, the speed is uniform but velocity is variable and hence it is an accelerated motion. This is a concept we are supposed to remember. Next time, we shall be talking about two important forces that act on an object in circular motion.